Problem number 3. Just note this problem, students. Note this problem. The end block of pre-stressed beam 250 mm wide and 500 mm deep in section is pre-stressed by two cables. Pre-stressed by two cables carrying forces of 450 kilonewton each. One of the cable is parabolic located 125 mm below the central line at the center of span and anchored at a point 125 mm above the central line at the ends. Okay, there are two cables. Okay, in that first cable is parabolic located 125 mm below the central axis at the center of the span and it is above the central axis at the support by a distance of 125 mm. And the second cable is straight located 100 mm from the bottom of the beam. Okay, second cable is a straight cable and it is located 100 mm from bottom of the beam. The distribution plates for the cables are 100 mm deep and 250 mm wide. Calculate the maximum tensile stress along the axis of the beam using IS code method. This is the question. So as there are two cables given in this problem, okay, there are two cables which are existing in the beam. For two cables, there will be two anchor plates, obviously. Okay, let us write the diagram first for the problem given. Solution. It is 250 mm wide and 500 mm deep, correct? Two 50 mm wide and 500 mm deep. Is pre-stressed by two cables carrying forces of 450 kilonewton each. Okay. Now let us write the profile of the cable in the longitudinal section of the beam. I'll write the longitudinal section now. Let us write the centroidal axis. Centroidal axis. Now write the cable profile. So one of the cable is parabolic located 125 mm below the central line and anchored at a point 125 mm above the central line at the ends. Okay, at support it is above the central line by an amount of 125 mm and at the center of the span the cable is at a distance of 125 mm below the central axis. It's a parabolic cable. Okay, here 125. 125 mm and at center also the cable is at a distance of 125 mm from central axis. Then coming to the profile of the second cable is straight located 100 mm from the bottom of the beam. From bottom of the beam. I'll write the straight cable now. And this straight cable is located at a distance of 100 mm from soffit of the beam. From soffit of the beam. Okay. Now, here distribution plate size is also given. Distribution plates for the cables are 100 mm deep and 250 mm wide. Okay. So as there are two cables, obviously there should be two distribution cables. Two distribution plates should be provided for both the cables. Okay, so here there will be one plate at this point, and for the straight cable there will be one more plate for anchoring the cable at the ends. Okay, now I'll write the distribution plates, and in the cross section I will show the distribution plate in the cross section, and size is given 100 mm deep and 250 mm wide. 250 mm wide means the width is equal to cross section only. Here one plate and here one more distribution plate. Okay. So this is the cable location. Here there will be cable at this point and this point. Okay. Deep depth of the plate is given as 100 mm and width is given as 250 mm. Okay, here also it is 100. This is the size of the plate. Okay, and length of the span of the beam is given as 10 meter. Let me mention that also here in the figure. 10 meter is the span of the beam. Span of the beam is 10 meter. Okay. Then pre-stressing force is given. How much it is given? 450 kilonewton. Let me take here. Pre-stressing force P is equal to pre-stressing force P is equal to 450 kilonewton, which is equal to 450 into 10 power 3 Newton. Okay. Now coming to the question, it is asked to find maximum tensile stress along the axis of the beam using IS code method. Okay, that is the question. Okay, to find maximum tensile stress. Okay, so we know the formula for maximum tensile stress. In yesterday's problems, we have solved for maximum tensile stress. Let me show you here. In some of the problem, we have calculated maximum tensile stress. I think in first or second problem. In second problem, let me see. Yes, here. Here we have the formula for maximum tensile stress. Okay, let me copy this formula. Let me copy this formula. We know that FV max, maximum tensile stress, is equal to FV max is equal to FC into 0.98 minus 0.825 YP naught divided by Y naught. This is the formula. Okay. Now to find this maximum tensile stress, what are the things we needed? We need YP naught and we need Y naught. We need YP naught and the Y naught. YP naught is nothing but it is depth of anchor plate. Okay, and it is given, how much it is given? 100 mm. YP naught is known. And Y naught is nothing but size of prism. Size of prism. Here, very important. Here we have two cables and two anchor plates. Two anchor plates or two anchor plates. There will be two different prisms, two different size of prisms for two different anchor plates. Okay. Therefore, let me write the diagram showing the prism, size of the prism. Here prism is nothing but the portion where we are providing this reinforcement. Okay, the portion of the end block is called as prism. Okay, in that portion only we are providing this reinforcement to resist the tensile forces or tensile stresses. There are two plates. This is the central axis. The one plate is 100 mm, means one cable is 100 mm. So this is cable 1 here. Here we have cable 1. Okay, at a distance of 100 mm from soffit of the beam. And here somewhere here we have cable 2. Cable 2 which is at a distance of 125 mm above the central axis. Okay, and for each cable there are anchor plates provided for each plate. Okay. Okay. Now the size of the prism will vary here. Okay. Size of the prism mainly depends on two factors. Correct. It mainly depends on two factors. One is width of the beam, and one more thing, the distance of the cable from nearest extreme fiber. Okay. Therefore, as the cables are provided at different positions along the cross section of the beam, the size of the prism will also changes here. Okay, let me show it by a dotted line size of the prism. This is the size of the prism for straight cable. Okay, similarly we get size of the prism for different size of the prism for the parabolic cable. Okay, and this is represented by 2y0 and 2y0, 2y0, 2y0. Okay, so why we are using this 2y0 notations and 2yp is, let me go to the theory part here. See here, students. Yes, here we can see why we are denoting these heights by 2yp0 and 2y0 means, see, with respect to centroid of the central axis of the plate, or with respect to the cable profile, or with respect to the central axis of the plate, we will study the distribution of the stresses. We will study the distribution of the stresses. Okay, so in the above portion, for above portion, okay, whatever the stress portion which is above the central axis of the plate, it is called as y0, and below the central axis of the plate, it is y0. That is why it is totally, it is taken as 2y0. Okay, similarly the yp0 we will use yp0 value above the central axis of the plate and yp0 below the central axis of the plate. Okay, we will study the stress distribution individually above the central axis of the plate and below the central axis of the plate. That is why we are denoting by 2y0 and 2yp0 instead of by just denoting it by yp0 and y0. Okay, I hope this is clear for everyone. Okay. Now, so this is cable 1 and cable 2. This is cable 1. This is cable 2. Okay. Now, what is the question? Question is to find FE max. FE max. Now, for both the cables individually, we will find the tensile stress. Okay. First, we will calculate for cable 1. Cable 1, we will perform the calculations. Okay. What are the things we need? We need FC. We need the value of FC. For getting the value of FC, first you do some initial calculation. Here the pre-stressing force P is given 450 kilonewton. Okay. And area of cable is also given. Area of cable is also given. Here you can see. Yes. P is equal to 450 kilonewton. And here I already written now 450 into 10 power 3 Newton. Okay, we will just directly perform the calculation for cable 1 and cable 2. Okay. Now we need the value of FC. FC is equal to what? FC is equal to P by AP. FC is equal to P by AP, where AP is area of the prism here. Okay. AP is nothing but area of the prism. So to get area of prism, we should know the value of this 2y0. Okay. We should know the value of 2y0. First, we will calculate the size of the prism. Okay, for cable 1, the depth of the plate is how much? Depth of the plate is, it is 100 mm. It is given in the problem. 100 mm. Nothing but it is 2yp0. Let me take that value. 2yp0 is equal to 2yp0 is equal to 100 mm, which is nothing but depth of anchor plate. Depth of anchor plate. Okay, 2y0 is equal to 100 mm. Then 2y0 or size of the prism. Size of prism. Nothing but 2y0 value we have to calculate now. There are two different calculations that we need to perform. First calculation is 2y0 is equal to 2y1, where y1 is distance of nearest extreme fiber from the cable, okay, or from the center of the plate. Okay. Okay. So y1 is nothing but distance of centroid of the plate from nearest extreme fiber. Okay. So here the distance of cable, okay, from the central axis is 125 mm. Therefore, here also it will be 125 mm. 125 mm because overall depth is 250 mm. Overall depth is 250 mm. Half of the depth is, so overall depth is 500 mm. Overall depth is 500 mm. 500 divided by 2 will give 250. Okay. 250. Therefore, distance of cable, parabolic cable at here at the support, I'm telling at the support from central axis is 125. Therefore, this nearest extreme fiber distance will be 250 minus 125, you will get 125 mm as distance. Okay, therefore 2 into 125 is equal to 250 mm. So this is the first calculation. Second calculation is just taking the width of the beam. 2y0 is equal to width of beam. Okay, width of beam, it is given as how much? Width of the beam is given as 250 mm. Yes, 250 mm. 250 mm. Okay, out of these two calculations, you need to take the least value. You need to take the least value. Therefore, we can consider 2y0 is equal to 250 mm. Okay, both are same values only. So 2y0 value becomes equal to 250 mm. Now you got the value of 2 yp0. You got the value of y0. Okay. Now you can calculate the FC, compressive stress. Okay. Therefore, the compressive stress FC is equal to P by AP. Okay. Processing force divided by area of the prism. Okay. Area of the prism, just now we have calculated the side of the prism, length of the prism 250 mm. Okay. So it is 250 mm here. Okay. 250 mm and 250 mm. So this will give area of this prism for the top anchor plate. Okay. Therefore, area of prism AP is equal to area of prism. So don't get confused, students, here. AP, do sometimes what you will do, you will take area of the cross section. That is wrong. AP is nothing but here area of the prism. Okay. So we know the side of the prism 250 into 250. Okay. So we'll get the answer as 62,500 mm square. 62,500 mm square as compressive stress FC. Now you got all the values, required values FC, yp0 and y0. Just substitute and get the answer. Okay, therefore, the tensile stress, therefore, the tensile stress is equal to Fe max is equal to FC into 0.98 minus 0.825 yp0 divided by y0. Okay. Therefore, FC now you calculate. After this, I forgot to calculate. FC is equal to P is equal to how much? 450 into 10 power 3. 450 into 10 power 3 divided by area of prism 62,500. If you solve for this, you will get the answer as 7.2 Newton per mm square. Okay. Now substitute here 7.2 is the compressive stress into 0.98 minus 0.825. Okay. Yp0 divided by y0. Yp0 is 100 divided by y0 is 250. 100 by 250. Okay. See, students, yp naught divided by 2y naught is nothing but yp naught divided by y naught only. Okay, so instead of dividing by 2 here, one instead of substituting 125 and here 50 and 125, I substitute directly because it gives the same answer. Okay, 2 yp naught divided by 2 y naught will be yp naught by y naught only. Okay, that's why I am substituting the same numbers. Therefore, Fv max is equal to it is, we will get it as 4.68 Newton per mm square. 4.68 Newton per mm square. Okay. Next, cable 2. Cable 2. Now we have calculated the tensor stress in the cable 1. Okay. Now we will calculate tensor stress in the cable 2. Same procedure. Here we have to follow the same procedure only. Okay. The plate dimension is same only. Okay. Plate dimension is same only. Therefore, 2 yp naught is equal to 100 mm only. 100 mm only. Okay. Then size of the prism. Size of the prism. Let us see. There are two calculations as we done for previous case. For previous cable, first cable, we perform the same calculation. First one is 2 y naught is equal to 2 into y1. Okay. For the second plate, okay, for second plate, the bottom fiber is the nearest extreme fiber from centroid of the plate. Okay, that distance is directly given. That distance is directly given here. It is a straight cable having a distance of 100 mm from socket of the beam. Okay, so this itself becomes the y1. Okay, at the beginning I have mentioned here y1 is equal to 100 mm. Okay, therefore here it is 2 into 100. 2 into 100, so 200 mm. 200 mm. Second one is 2 y naught is equal to width of beam, which is equal to 250 mm. Okay, so this is the least value. Least value. So therefore, the size of the prism 2 y naught is equal to 250 mm. Is equal to 250 mm. Okay. Now area of the prism, we can calculate area of prism. Therefore, area of prism is equal to AP naught, or AP is equal to 2y naught into 2y naught, or 250. Sorry. Here 200 mm least value. Sorry, least value you have to take now. 200 mm. 200 by 200. So it will give 4 into 10 power 4 mm square. Okay. So out of these two calculations, 200 mm is the least value. Therefore, size of prism is taken as 200 mm. Area of prism is equal to 200 into 200, which gives 4 into 10 power 4 mm square. Okay. Now, compressive stress we can find. Compressive stress is equal to compressive stress is equal to compressive stress is equal to FC is equal to P by AP. Okay. Pre-stressing force is 450 into 10 power 3 Newton. Area of prism is 4 into 10 power 4. Therefore, FC value is 11.25 Newton per mm square. 11.25 Newton per mm square. Okay, now we can find the tensile stress. Therefore, tensile stress is equal to FC into 0.98 minus 0.825 into yp naught divided by y naught. Now you have to substitute the corresponding FC, yp naught and y naught value here. FC is 11.25 into 0.98 minus 0.825. Yp naught. Yp naught is 100 and y naught is 200. 100 by 200. 100 by 200. Therefore, the answer is Fe max is equal to 6.38 Newton per square. Okay, so this completes the problem, students. Okay, so as there are two anchor plates, as there are two cables, obviously there will be two different anchor plates for the cables. For two different anchor plates, we have to individually find the tensile stresses corresponding to cable 1 and cable 2. The procedure is very simple. Initially, you have to find yp naught value, which is nothing but depth of anchor plate. It is given in the problem only. You need to find the size of the prism. Knowing the size of the prism, you can find the compressive stress. Okay, that is the ratio of precessing force to that of size of the prism. Knowing the FC and Y naught and YP value, just substitute in this particular problem, particular formula, you will get the tensile stress value. That's it. Okay. So if you have any doubts at any point of calculation, you can ask, friends. Thank you. We'll move on to the next problem. Okay. I got confused. The data given. Here, make some changes here in the problem. Write this problem. This problem we have already solved, okay, in the previous class. We already solved in the previous class. Write this problem, all of you. Problem number 4. It is also a problem on a rectangular beam. The end block of a post tension beam is 150 mm by 300 mm deep. The cable comprising of 3 members of 12 7 mm dia and stressed to 1200 Newton per mm square. Okay, so the beam is a rectangular section. One 50 by 300. 150 by 300. A cable comprising of 3 members of 12 7 mm dia and stress to 1200 Newton per mm square. Okay, there are 3 members. 3 members. Okay, and each member is having a 12 number of 7 mm diameter bars. Okay, each member is having 12 number of 7 mm diameter bars. Okay, therefore the area of cable will be how much? Therefore the area of cable is equal to, there are 3 numbers and there are 3 members and each member is having 12 number of 7 mm dia bars. So area of one bar will be 5 into 7 square by 4. Okay. If you calculate the answer, you will get it as 1385.44 mm square. Okay. Area of cable. Stress in the cable is given 1200 Newton per mm square and stress to 1200 Newton per mm square. Pre-stress is given. Pre-stress is equal to 1200 Newton per mm square. Stress in the cable is given. Area of the cable we have calculated. You can calculate the pre-stressing force. Therefore, the pre-stressing force is equal to P is equal to stress into area of cable. Area of cable. Stress is 1200 into 1385.44. Therefore, pre-stressing force is equal to 1.66 into 10 power 6 Newton. Okay. Then moving ahead, is anchored against the end block at 100 mm from soffit of the beam. Okay. Let me write the central axis. Central axis. Okay. What it is said here? The anchor plate is 75 by 75 mm. Okay, anchored against the end block at 100 mm from soffit of the beam. Okay, and size of the plate is 75 by 75. Here we'll have the cable at the center. Okay, size of the plate is 75 by 75. 75 by 75 and is anchored against the end block at 100 mm from soffit of the beam. The cable is at a distance of 100 mm from soffit of the beam. Okay, from here, which is nothing but y1, distance of cable from nearest extreme support. It is given as 100 mm. 100 mm. Okay. Next, the cable bears on the plate through. Okay, just go through it. The cable bears on the plate through a female cone of 30 mm diameter. Okay, the cable is carried through a female cone. Let me write the diagram. In the longitudinal section, we can show it clearly. This is the plate. Okay. Okay, the cable is carried through a female cone. like this. Okay, all the cables are carried through this female cone. Okay, and the dia here is 30 mm. Is 30 mm. Female cone of diameter 30 mm. Okay, that is what the meaning. Okay, the cable bears on the plate through a female cone. Okay, the cable is carried through a female cone having 30 mm diameter. Okay, the question is to find the thickness of the anchor plate. We need to find the thickness of the anchor plate here. Thickness of the anchor plate. And design the anchorage reinforcement. Reinforcement should also be designed. FCK is given. Okay, and permissible shear stress is given. I'll write the given data. FCK is equal to 30 Newton per mm square, and shear stress on the plate. Shear stress on the plate is how much it is given? 100 Newton per mm square. 100 Newton per mm square. And it is asked to use Fe 415 grade steel for design of the reinforcement. Fy is equal to 415 Newton per mm square. 415 Newton per mm square. Okay. So here we need to perform two things. First is to calculate to design the end block, and second thing is to find the thickness of the anchor plate. Okay. Now we'll go stepwise. Initially, first you find size of the anchor plate. A size of anchor plate. It is given in the problem only. Anchor plate. Size of the anchor plate. Nothing but 2 IP naught. It is given. 2 IP naught is equal to this is only 2 IP naught. Okay, it is given as 75 mm. 2 IP naught is equal to 75 mm. Okay, so after finding the size of the anchor plate, next you find size of the prism in the second step. Size of prism. Size of prism. So there are two calculations we need to perform. First one is 2 yp naught is equal to 2 into y1. Okay, y1 value is given. It is 100 mm. Okay, distance of nearest extreme fiber from the cable point. Okay, 2 into 100, which gives 200 mm. 200 mm. Then second calculation is, so this is 2y0. 2y0 is equal to beam width. Beam width, which is equal to 150 mm. Which is equal to 150 mm. So out of these, this is the least value, 150 mm. Least value. Therefore, take size of prism 2y0 is equal to 150 mm. Okay. So to design the reinforcement, we need the bursting force, correct? To design the reinforcement, we need bursting force. Therefore, first you find bursting force. Bursting force FVST. Okay, we have the formula for bursting force in the code book, correct? I have not opened. In page number 36, it is available. Okay, in page number 36 of IS 1343 code book, it is available. Okay, therefore we have the formula that is FBST divided by stressing force Pk is equal to 0.32 minus 0.3 Yp naught divided by Y naught is the formula which is available in page number 36 of IS 1343 1980. Okay. Therefore, the FBST force is equal to Pk into 0.32 minus 0.3 Yp naught divided by Y naught. Okay. Stressing force is given. We have calculated it. That is 1.66 into 10 power 6. 1.66 into 10 power 6 into 0.32 minus 0.3 into Yp naught is 200. Sorry. Yp naught is 75 and Y naught is 150. 75 by 150 into 75 by 150. Okay. Therefore, FBST bursting force is equal to 282.2 into 10 power 3 Newton. You'll get this answer. 282.2 into 10 power 3 Newton. Last step is, which is the next step? After knowing the bursting force, you can design the reinforcement or you can find the area of the steel required for the end block. Next step, area of steel. Area of steel. Okay. We have the formula for finding the area of steel. Area ST is equal to EST is equal to FBST divided by 0.87 Fy. Okay. Therefore, 282.2 into 10 power 3 Newton is the bursting force divided by 0.87 into 415. Okay. Therefore, area of steel required is equal to 781.61 mm square. 781.61 mm square. Okay. Now you got the area of steel, some diameter of the bars, and find the number of bars. Okay. I will assume 10 mm diameter bars, assuming because area of steel required is more. Assuming 10 mm dia bars. Assuming 10 mm dia bars, number of bars is equal to number of bars is equal to area of steel divided by area of one bar. Area of one bar. Total area of steel required divided by area of one bar will give number of bars. So area of steel required is how much? 781.61. 781.61 divided by area of one bar 5 into 10 square by 4 will give number of bars. So if you calculate the answer, you will get around 9.95 as answer. So you can round it up to 10 numbers. You can round it up to 10 numbers. Okay. Now you can write the reinforcement details. Reinforcement details. Here a gap of 0.2 Y naught should be left here. Okay. Now mention the reinforcement. Here it is 2y0, 2y0. So the reinforcement we got is 10 numbers in both directions. Ten numbers of 10 mm dia bars in both directions. You have to provide in both directions. In both directions. So if you read the cross section, you need to provide total 10 numbers. Okay. Ten numbers in both directions. Okay. This is how we can write the reinforcement details. Now we have designed the reinforcement. Okay. We have designed the reinforcement. Design of anchorage reinforcement is over. We have left with one more question, that is to find the thickness of the anchor plate. To find the thickness of the anchor plate. Next, E, thickness of anchor plate. Okay, thickness of anchor plate. To find thickness of anchor plate. Okay, so this thickness of anchor plate is determined based on the diameter of the cone. The thickness of the anchor plate depends upon mainly two things. One is the punching force and the diameter of the cone here, which is attached to the plate. Okay, let me read the small cross section here. So this is the anchor plate. Okay, this is the anchor plate. So in this we have diameter of the cone, diameter of the cone. So the dimension of the anchor plate is how much? It is 75 by 75. 75 by 75, and diameter of the cone is given as 30 mm. 30 mm. Okay. Now we have to find the thickness of the anchor plate. First we will find what is the punching force that will act on the plate. Punching force is equal to punching force that is acting on the plate is equal to pre-stressing force only. It is equal to pre-stressing force only. Say the same force. Okay, it is considered. So here to find the thickness of the plate, it is considered as punching force. Instead of calling pre-stressing force, we will call it as punching force. And it is known how much it is. Punching force 1.66 into 10 power 6 Newton. 1.66 into 10 power 6 Newton. Nothing but pre-stressing force only. Pre-stressing force only. Okay. Now we got the punching force. Now whatever the plate, whatever the thickness of the plate which we are giving, it has to resist the shear stress which is acting on it. The shear stress which is acting on it. Okay. The shear stress of the plate is given. Okay. Shear stress capacity of the plate is given. How much it is given? 100 Newton per mm square here. Okay. Shear stress in the plate, the maximum limiting shear stress in the plate, shear stress in plate is given as 100 Newton per mm square. 100 Newton per mm square. Okay. The maximum limiting stress in the plate. If you know the shear stress in the plate, you can find the resisting force in the plate. Resisting force is equal to see, the punching force is acting over this periphery, correct? Okay, the punching force will exist along the periphery of the cone on the plate. Okay, therefore this resisting force is equal to the area of the plate which is resisting into shear stress. Okay, the area or portion of the plate which is resisting is the circumference multiplied by thickness. Okay, I hope you are understand. That is the area in which is subjected to shearing action. Okay, the circumference into thickness of the plate will give area in which the shear stress is acting on the plate. Okay, I hope you are understanding. Therefore, here circumference into thickness of the plate. Circumference into thickness of the plate will give area of the plate which is subjected to the shearing action. Circumference multiplied by thickness. Thickness is perpendicular to the screen here. Okay, will give area of the plate which is subjected to the shearing action into shear stress. Into shear stress will give resisting force. Okay, circumference of the this circle is pi into d. We know the formula, into t into shear stress. Okay, therefore it is pi dt into shear stress is given, it is 100 mm, 100 Newton per mm square. Okay, now whatever the punching force which is acting on the plate, if it is equal to the resisting force, okay, then only the plate will be in a safe condition. Okay, now we have to equate the punching force. Therefore, equating the punching force and resisting force Okay, punching force is how much? Punching force is 1.66 into 10 power 6. Punching force is equal to resisting force. Okay, this resisting force should be equal to the punching force. Okay, then only plate will be in safe condition. The punching force is 1.66 into 10 power 6. 1.66 into 10 power 6 is equal to resisting force is how much? Just before we have calculated, it is pi dt into 100. Pi dt into 100. Okay. Diameter of the cone is given. D is equal to 100 mm. It is given as 100 mm. Just substitute here. Sorry, 30 mm. Diameter of the plate is 30 mm. As it is 30 mm. 30 mm. 30 mm. Substitute here. Therefore, 1.66 into 10 power 6 is equal to pi into 30 into t into 100. Okay, only the thickness is unknown factor here. By this, we'll get the thickness of the plate. T is equal to, if we solve for it, we'll get the answer as 176.13 millimeter as answer. Okay, we can round it up to 180 mm. Okay, below you can write. Therefore, provide the thickness of anchor plate. Thickness of anchor plate T is equal to 180 mm. Okay. So this is how we find the thickness of the plate required. Okay. Thickness of the plate required depends on the punching force or the pressing force acting on the plate and the diameter of the cone which is attached to the plate. Okay. So this completes the problem. If you have any doubts, you can ask. Thank you. So we'll move on to the last problem of this model. Last problem. It is also similar kind of a problem. Okay. It is also similar kind of problem. But the position of the cable or the position of the anchor plate given is different here. Okay, just go through it. The end block of a post tensioned beam is 300 mm wide and 400 mm deep. Okay, so it is a rectangular section. Again, solution. It is a rectangular section having 300 mm wide and 400 mm deep. Mm and 400 mm deep. Okay. A pre-stressing wires 12 mm diameter and 10 number are stressed to 1200 Newton per mm square. Total area of cable you find it now. Area of cable is equal to, there are 12 there are total 10 numbers. Okay, in each number there are 12 number of 5 mm diameter bars. Therefore 10 into 12 into 10 into 12 into 5 into 5 square by 4. Okay, which gives 2356.19 mm square. Okay, then pre-stress in the steel is given 1200 Newton per mm square. Pre-stress is equal to 1200 Newton per mm square. Then the wires are located at a constant eccentricity of 100 mm below the central axis. Okay, write the longitudinal section of the beam. Write the longitudinal section of the beam and write the central axis as well. Okay, the cable profile is given as at a constant eccentricity of 100 mm below the central axis. I'll write the cable now. Okay, constant eccentricity of 100 mm below the central axis. Okay, design the end block and detail the reinforcement. If the anchorage plate is 200 by 200 and the size of the anchorage plate is given 200 by 200, write it. 200 by 200 means it will be of this length, correct? Because overall depth is 400. 400 divided by 2 is 200.
Okay, so here above the cable it is 100 mm. Below the cable we will get only 100 mm. Here 100. That is nothing but y1. Therefore, the cable the plate will come to the full length, full half of the depth of the beam. Okay. This is the cable plate having 200 by 200 dimension. Okay. If the anchorage plate is 200 by 200 and dia of the duct is 100 mm, dia of the duct is 100 mm. So here, as it is a post tension beam, duct is provided. Okay. Okay, dia of the duct is 100 mm. 100 mm. Okay. So in the longitudinal section, it will look like this. Okay. The dia of the duct is 100 mm. Okay. So you will get the y1 value here. Y1 means distance of the nearest extreme fiber from cable. It is total is 200. 200 divided by 2 is 100 mm. Or directly it is given cable. It is situated at 100 mm from central axis. Therefore, from bottom fiber it will be 100. Y1 is equal to 100. And eccentricity is given as 100. Okay. So this is what the given data. The question is similar to the previous problem, to design the anchor plate and to design the thickness of the anchor plate and the reinforcement for the end block. Okay, we have to follow the same steps as we have followed for the previous problem. First one is size of the anchor plate. First step, step A, size of anchor plate. Size of anchor plate, which is nothing but 2 yp0. It is taken as depth of the plate. How much it is given? It is given as 200 mm. 200 mm. Then step B, size of the prism. Size of prism. Size of the prism. We have to find it in two ways. First one is size of prism 2y0 is equal to 2 into y1. 2 into y1 is 100 mm. 100 mm. You will get 200 mm. And second one is width of beam. Size of prism 2y0 is equal to width of beam. How much it is given? Width of the beam? It is given as 300 mm. 300 mm. So out of these values, 200 mm is the least value. Okay, we have to take least value for fixing the size of the prism. Therefore, take size of the prism 2y0 is equal to 200 mm. Now size of the prism is fixed. That is 200 mm. Next step is bursting force. Finding the bursting force. C bursting force. Bursting force. We have the formula in page number 36 of IS 1343. That is FVST divided by Pk is equal to 0.32 minus 0.3 yp naught divided by y naught. Okay, page number 36. Okay, therefore, FBST is equal to Pk into 0.32 minus 0.3 yp naught divided by y naught. Okay, Pk is nothing but pre-stressing force. How much it is? Pre-stressing force. See, pre-area of cable is given, pre-stress is given, you can find the pre-stressing force. Here only I find it. Pre-stressing force. Force is equal to stress into area of cable. Stress into area of cable, which is equal to stress is 1200, area of cable is 23 by 6.19, which gives pre-stressing force as 2.83 into 10 power 6 Newton. Okay, so here it is equal to, the notation is same. The notation given is Pk, nothing but pre-stress only. How much it is? 2.83 into 10 power 6 Newton. Okay, therefore FBST is equal to 2.83 into 10 power 6 into 0.32 minus 0.3 into yp naught is 200, y naught is 200. 200 by 200. By this we'll get the bursting force. I will get it as 56.6 into 10 power 3 Newton. 56.6 into 10 power 3 Newton. Okay. Now, area of steel, we can find, if you know the bursting force, you can find the area of steel easily. Step E, area of steel. Area of steel. See, grade of steel is given, not given, correct? We'll assume Fe 415 steel only. Assuming Fe 415 steel. Assuming Fe 415 grade steel, Fi becomes 415 MPa. We know that area of steel, AST is equal to, what is the formula? Bursting force FBST divided by 0.87 Fi is the formula. So FBST is 56.6 into 10 power 3 divided by 0.87 into 415. By this we'll get area of steel. You will get it as 156.76. 76 mm square. So it is, which is a very low value. Therefore, we will assume some lesser diameter of the bars. Assuming 6 mm dia bars. Assuming 6 mm dia bars. Number of bars will be equal to area of steel divided by area of 1 bar. Area of 1 bar. Total area of steel divided by area of 1 bar will give number of bars. That is 156.76 divided by area of 1 bar, 5 into 6 square by 4. Okay, which gives around 5.54. You can round it up to 6 numbers. You can round it up to 6 numbers. You can write the reinforcement details as well. Okay. Cross section also you can write. How many numbers? 6 numbers, correct? 6 numbers. 6 mm dia in both directions. In both directions. Okay. So we have designed the reinforcement, students. One more thing we have to find, that is anchor plate thickness, correct? We will find it now. Anchor plate thickness, last step. So we have to follow the same steps that we have followed for the previous problem. Thickness of anchor plate. Thickness of anchor plate. Okay, we know the punching force. Punching force, which is nothing but pre-stressing force only. How much we got here? Pre-stressing force. It is 2.83 into 10 power 6 Newton. 2.83 into 10 power 6 Newton. 10 power 6 Newton is the punching force or the pre-stressing force. Then resisting force we can calculate now. Resisting force is equal to, similar to the previous problem, circumference into T into shear stress. Into shear stress. Circumference of the duct. Diameter of the duct is, circumference is nothing but pi into D. Pi into D into T into shear stress. Shear stress is given in the problem. How much it is given? Shear stress. Shear stress, permissible shear stress in steel is 94.5 Newton per mm square. into 94.5. 94.5. Okay, and diameter of the duct is 100 mm here. Diameter of the duct is 100 mm. Therefore, pi into 100 T into 94.5. Now, by equating punching force to that of resisting force, we will get the thickness of the plate. Therefore, equating punching force and resisting force. Punching force is pre-stressing force 2.83 into 10 power 6. 2.83 into 10 power 6. Resisting force is 5 into 100 T into 94.5. Okay, 94.5. Now, you will get the thickness of the plate required. Thickness of the plate required. If you solve for it, you will get the answer as 95.32 mm. You can round it off to 95 mm or 100 mm. Okay. Therefore, provide the plate thickness. Therefore, provide the plate thickness is equal to T is equal to 95 mm. Okay. So to this problem is over, friends. Any doubts you can ask. Thank you. To this fifth model is also over, and the design of pre-stressed concrete elements subject is also over, students. Thanks for your cooperation and support, and I wish you all the best for your examinations. Okay. So to this, I will end this session, students. Thank you very much. Thank you all. And wish you all the best for your examinations. Thank you.